Hello, welcome back. We're at the second part of Chapter 3. And Chapter 3 is about stoichiometry, nomenclature in stoichiometry, that's chemical accounting. So let's get more into it. We talked about nomenclature. Let's go and talk about chemical accounting. So formula mass. So we learned about moles in Chapter 2, and we learned about it with atoms. So what about molecules when you have moles of molecules? So first skill set we'll do is how to calculate the formula mass. It's the number of the elements, and so when you look at something, and I'm talking about this in terms of the example here, glucose. So glucose C6H12O6. So the number of elements in the first element of the chemical formula. So the C6, that 6 there means that there's 6 carbons. Likewise, the 12 underneath the subscript of hydrogen means there's 12 hydrogens, and the 6 underneath oxygen means there are 6 oxygens. So for this one here, we would then do 6 times the molecular mass of carbon. Carbon, in look at the periodic table, right here, it is 12.01. I'm going to abbreviate to 12, plus 12 times the molecular mass of hydrogen, which is 1.008. It's close to 1. And then plus 6 times, I know the multiplication sign is not needed around the parentheses, but 6 times the molecular mass of hydrogen, which is 16. If you add these up in your calculator, it turns out to be 180 grams per mole. So that's abbreviated. I guess I should do the long way. What the heck? 12 point says 12.01, 1.008, 16.00. So that's. So I will calculate that out for you. Okay, I'm back, and I've put that in my calculator. If you want to do exactly all the way through, I think it was 180. Okay, so how do we do this in terms of uh, comparing of, so we've learned, about number of molecules and that with atoms. Let's do that and further it for molecules. So aspirin ironically has a mass of 180 grams per mole too, but we can calculate it out. So let's do C9H8O4, and you do not have to memorize the periodic table. I've got a lot of it memorized because I am a chemistry god. And you can too. 9 times 12.01 for carbon, plus 8 times 1.008 for hydrogen, plus 4 times 16.00 for oxygen. And let's go ahead and do this in front of you. So, embarrassing seeing me do math. Watching me put the wrong numbers in the calculator. So this is what I was sparing you before. Oop, that's a plus sign. Times 60. 180.154. Of course, we only know it to this much by sig figs. All right, so aspirin contains 325 milligrams acetylsalicylic acid. How many acetylsalicylic acid does it contain? So we would do dimensional analysis. So start with the left. So 325 milligrams. So milli means 1/1000th. So it's a gram to 1,000 milligrams. Actually, grams acetylsalicylic acid, but I don't want to write all that stuff out. Then we have molecules. So mole acetylsalicylic acid, I should say just AS for aspirin. Grams aspirin, mole aspirin to 180.15 grams aspirin, and then 6.02 times 10 to the 23rd molecules. There's aspirin to moles aspirin. And then you throw in your handy dandy calculator, which I'll pause. Okay, I'm back, and I throw in the calculator, and I get 1.086 times 10 to the 21 by 3 sig figs, 1.01 times 10 to the 21 acetylsalicylic acid molecules. Molecules of aspirin. So, what about the ibuprofen? So, pause the video and try this yourself. Okay, whoa, that was fast. Okay, so if you did the proper setup, I'm abbreviating here. So 200 milligrams, same thing as 0.2 grams, and the molecular weight for that is 206 grams. So divide by the molecular weight to get moles, and then Avogadro's number to get the molecules. And the second question is a trick. So looking at it, so 13 carbons plus 18 hydrogens plus 2 oxygens means 33 atoms. So you just multiply the answer by 33 and you get 1.92 times 10 to the 22 total atoms. Okay, so what else can you do? And what we're doing here is trying to build, what can we tell from formula? What kind of information are they giving us? We can also figure out mass percent. So for instance, what is the percent chlorine in Freon 112? So freons are an example of CFCs, and CFCs are chlorofluorocarbons. So what are chlorofluorocarbons? They are molecules that contain chlorine, fluorine, and carbon only. Can you guess what hydrocarbons are? They're molecules that have hydrogen and carbon only. Right now, we tend not to use CFCs. Instead, we use fluorohydrocarbons. Can you guess what are in fluorohydrocarbons? Fluorine, hydrogen, carbon. So, actually, the names tend to make sense. So, but let's go ahead. What's the percent chlorine in C2Cl4F2? So the percent of that, so akin it to like body fat percentage. What's your body fat percentage? It's the amount of fat that you have over your total body weight. So the percent chlorine, it's going to be the mass chlorine over total mass. And what I've just derived there, that's considered chemistry common sense. So being able to figure out the percentage of something and figuring out the formula, that is something that you should know how to do. So at this level of education, you should know that. That's considered common sense. So the mass of chlorine, this is going to be 4 times chlorine. Chlorine is 35.45 grams per mole, divided by the total mass of the molecule, which is 2 times 12.01 plus 4, and still the chlorine, 35.45, plus then the mass of fluorine, 2 times 19 for the fluorine. And then the times it by 100%. So let me calculate that out for you. I'm back, and I moved. Okay, calculating that out, and looking at the calculator, this is going to be 69.7. I mean, I guess I'm going to do 57. 57%. And some things to note here on the dividing thing. So if you notice, I put a parentheses here. That is because I needed to be able to include this whole thing and underneath the denominator for that. So it's important to put that parentheses in. So keep that in mind. Remember, computers are smart, but they're only as smart as what we can put in. Okay, so again, point of this, we're going to learn what else we can tell from formula masses. And you like, you know, this is kind of boring. At least I like the fun part of chemistry is like the quantum mechanics stuff. That's a lot of fun, and like when you're discovering new things, that's a lot of fun. This is just something. These are the skill sets you have to do to be able to do the other stuff. So, well, maybe you're having fun. I think a lot of stuff is more interesting, but this is still important. It's part of the building blocks for other stuff, and this stuff you will use not only in this class but many other classes. And other stuff too, like the acids and base stuff. You will use that in many other classes. But okay, let's look at this one. Hydrogen may potentially use in the future replace gasoline as a fuel. Probably not, but we'll see. Most major automobile companies are developing vehicles that run on hydrogen. That's true. These cars are environmentally friendly because their only emission is water vapor. One way to obtain hydrogen for fuel is to use an emission-free source such as wind power form elemental hydrogen from water. What is the mass of hydrogen in grams is obtained from 1 gallon of water? Okay, so this is not how we get hydrogen, though. You can get hydrogen this way, where we get hydrogen. Well, the idea is that well, 1 gallon. So hydrogen, H2O. Actually, you can do 2H2O. Using electricity, you can break this apart to form 2 hydrogen gases plus 1 oxygen gas. So that's how they get oxygen in nuclear submarines. How we get hydrogen in industry today is we use something called steam reformation, which you take steam and react it with methane, CH4, to get hydrogen. Or you can do it by reforming molecules in a refinery. They change the shape of the molecule, hydrogen pops off. Those are the two main sources of hydrogen. We don't get it from water. But hydrogen, some cars use hydrogen. It's just it doesn't carry a lot of energy with it. Per mass it does, but per volume not so much. So there are much better alternatives than hydrogen. But sorry if I'm talking about this. I mean, some things do run off of hydrogen, especially things that need to be light. Like rockets, they need to be light. They'll run off of that, but that's because they want to be light. If you had an airplane that runs off of hydrogen, it would have to have much bigger wings to contain the fuel, have a smaller cabin. So those are the drawbacks of having hydrogen. And the other thing with hydrogen is explosive, so very explosive. So if you have a car accident, it could really cause a big explosion. So, but anyways. That's just, drawbacks of fuels. Okay, so 1 gallon of water. So again, we use dimensional analysis. So we start off with 1 gallon of water, and then we can convert. So how do we get to grams? Well, we can do 3.78 liters of water per gallon of water. I'm not going to write the water. So liter water, gallon water. And there is 1 kilogram water per 1 liter of water. So, it says that 1 gram. I'll do it the other way. I'll follow the way I do it in the book. So, 1,000 milliliters per liter. That's water. And then 1 gram per milliliter water. And I know I'm saying the words water because it's 13.8 grams mercury per milliliter of mercury, but I just don't want to write water a lot of times. Okay, and then what else? So then we have to do the density percent. So water, so H2O, water is, so percent hydrogen is 2 times 1 all over 2 times 1 plus 16 times 1. So this is the 2 hydrogens over the 2 hydrogens plus 1 oxygen. That's it. I'll put the other X for oxygen. So it's 2 over 18, or 1/9, which is 11%. So how many sig figs? So 11.1% hydrogen. So per gram water. Per gram water. So percent hydrogen. So, or if you want to do the fraction, however you want to do it, I would just multiply by 11%, but okay, we can do 1/9. So 1 part hydrogen to 9 parts water. So 1/9 or 11%. And, okay, and then you put that in your calculator. Okay, and the answer is 420 grams of hydrogen. I put the H2. It's hydrogen element or H. It's in the form H2, but either way, it's 420 grams of hydrogen. And if you notice something here, I've really simplified the calculations. I've just said 3.78 times 1,000 divided by 9. So, I mean, I'm kind of hardwired whenever I think in terms of what's the fewest keys I can stroke in my calculator. And the reason for that is twofold. Number one, it limits mistakes by putting the wrong numbers. The second thing is I'm used to taking tests that are timed. So I just kind of have it hardwired in me to think, okay, what's the fastest way I can do this? So now, obtaining empirical formula from experimental data. This is called, empirical formula is the lowest ratio of atoms. So now watch out for something. So C6H6 and C2H2. C6H6 is also known as benzene. C2H2 is also known as acetylene. Benzene is a liquid. Acetylene is the stuff they use in blow torches for welding. So they are very different compounds, but they both have the empirical formula of 1 carbon to 1 hydrogen. So that's a caution with this. It tells you some information, not all of the information, but let's go through it. A compound containing nitrogen and oxygen is found to produce 24.5 grams nitrogen and 70 grams of oxygen. Calculate the empirical formula of the compound. As we're doing this chapter also, we're going through the history of chemistry. A long time with chemistry was just, what's in this stuff? And so we'd see what elements are in this stuff. And oxygen was a hard thing. Actually, oxygen, they typically figure out the molecular weight of something, and then the missing mass they put in for oxygen. So oxygen was hard to find. Now we just throw things in a mass spec, it breaks apart, and then we can sort it out. So we did some tricks there when we were figuring out chemistry. Okay, so let's do this though. We produced 24 0.5 grams nitrogen. So we start here, 24.5 grams nitrogen. And so we're going to figure out the moles. The grams don't mean much. Moles nitrogen to 14 grams nitrogen. And let's do oxygen to 70, I know 0.0 grams oxygen, mole oxygen per 16 grams. So I'm going to go ahead and talk to you while I sort this out in the calculator because I don't want to feel lonely. Do you ever watch Bob Ross? I feel like a chemistry Bob Ross right now. I should. Happy little molecules. Happy little molecules. So we get 1.75 moles of nitrogen, and then we have 70 divided by 16, and we get 4.375. We're like, we're done! No, we're not. So now what we got to do is got to divide both sides by 1.75. And we do that to get the lowest ratio. And 1.75 divided by 1.75, that's easy. But oxygen, let me divide that by 1.75. And then we have 1 mole nitrogen to 2.5 moles oxygen. And you're like, I'm done. I'm done and I'm happy. So now I go, so it's N1 O2.5. This is actually wrong. So when you deal with molecules, you have to deal with something called discrete mathematics, which means only whole numbers count. So only whole numbers count, and the discrete mathematics mean you have to multiply it by a factor to get rid of the fraction. And so if you think of a half is 0.5, a third is 0.33, a quarter, 1/4 is 0.25, a fifth is 0.2, and so on. So what we have to do is to multiply this by 2, and we get N2O5. Now this is indeed then the empirical formula. So remember that for molecules, you cannot have fractional atoms. What does a fractional atom work out? So this right here, like the N2O5, this works for some averages. Maybe you've seen like the average couple has 1.5 children. Can you tell me what 1.5 children means? Another example, I was doing when I was an intern for Bath and Body Works and Victoria's Secret. They're a company called Intimate Brands. Either way, we were making candles, okay? And I was doing industrial engineering. I was calculating out the number of people that we need on each line, and I got something like I needed 2.7 people at this line, which means I needed 3. And you can't round down either. If I needed 2.2, I would still need 3 people. But you might want to put your worst workers there, though, or something like that, because put the more efficient workers somewhere else. But what I mean by that, so like you can't have a fraction of a person, you can't have a fraction of an atom. So whatever calculation you have, you can average things out to a certain amount, but in the world of chemistry, like in the world of humans, you got to multiply it up. Get rid of the fractions. Okay, so ibuprofen, this is for you to work on. If you remember, it was in the previous example up here. It's C13H12O2. So work this out, and you can get C13H12O2. Is that H12? H18. Sorry. C13H18O2. So, okay. Moving on then to talk about balancing chemical equations. So chemical equations is kind of like a recipe, but it gives you quite a bit of information. So this one here, we have methane, CH4, plus 2 diatomic oxygens makes carbon dioxide and 2 waters. So you haven't learned about what the shape of the molecules are yet, but notice a couple of things. The number and type of each atom is the same. So if you look at the hydrogens, there are 1, 2, 3, 4 hydrogens there. I marked in blue. And there are 1, 2, 3, 4 hydrogens there, again marked in blue. So 4 hydrogens on both sides. Oxygens, 1, 2, 3, 4. Oxygens on the left, 1, 2, 3, 4. Oxygens on the right. So that's all even. And then the carbon, 1 carbon here, 1 carbon here. So you see that the same number and type of each atom is the same on both sides. And also note a few things. So right here, CH4, there is the same formula. So 1 carbon, 4 hydrogens. And 2 oxygens, these have 2 separate oxygens. And CO2 and H2O. So like for instance, if you have the equation CH4 plus O2 to CO2 plus H2O, why don't let's see here, there's 4 hydrogens on the left and there's only 2 on the right. So why don't we just call this H4 and then get rid of the oxygen, right? So CH4 plus O2. Now we made CO2 plus H4. I'll write that more clearly. And then say, okay, I'm done. I balanced it. Well, not really, because you've changed this. It's no longer what you originated. You have to keep what it was to start off with. So it's got to stay water. Okay, so let's do an example. And C4H10. So C4H10, how you balance this? Well, you pick an atom and then you carry it on through. So 4 carbons here, do 4 carbons here. Okay, let's look at the hydrogens. So there's 10 hydrogens on the left. So 5 times 2 makes 10. So 10 hydrogens on the right. Then for oxygens, okay, so oxygen, there's 2 on O2, so 2 on the right. So we have 4 O2, so we have 8 oxygens here. And then we have 5 and the 5 H2Os, 5 oxygens there. So add them together, and we get 13 oxygens. And you can see there's already a problem here because there's an odd number. And the odd number, so you can do 6.5 oxygens. And you might actually see some equations written out this way, but that's truthfully improper. So what you should do is multiply everything by 2. So multiply the whole equation by 2, you get 2 butanes, 13 oxygens, 8 CO2s, and 10 waters. So now this is properly balanced. And you can check to see the same number of atoms on each side. So for butane C4H10, 2 times 4 is 8 oxygens, 8 CO2s, 8 oxygens there. 2 times 10 for the hydrogens in butane, 10 times 2 for the hydrogens is also 20, so 20 equals 20. Oxygen 13 times 2 is 26. And then O2, so that's 8 times 2 is 16. 10 times 1 for the water is 10. 16 plus 10 is 26. 26 equals 26, same number of oxygens. So that's the way you balance the chemical equations. You look to one element and you carry it on through. And this next one here, so this is meant to be done at home, but I'll show you a couple tricks here. So the number of waters in the balance equation. When you look at a multiple choice problem, one of the things you want to do is discount things. So right away, 6.5 is wrong because it's discrete mathematics. What does a half of a water look like? That doesn't make any sense. So it has to be whole numbers. So now you whittled it down to 3 choices. So let's try balancing it. So C6H13, so get a 6 here. Okay, and then we can't do there's an odd number of hydrogens, so let's just go ahead and multiply this by 2, make 12. Looks like 72. 12. Okay. So now we have 26 hydrogens, so now we have 13 waters. You're like, oh man, got to multiply again because we have an odd number, so I got to multiply it by 2 again. So 4 and 24, and 13 times 2 is 26. So now we're going to have an even number. So 24 times 2 is 48 oxygens, so it's just right here, 48 oxygens there, and then 26 oxygens there. So another thing to do is 24 plus 13, this will be 37. And 37 oxygens there. Or you can multiply, you can add 48 plus 26 divided by 2, and you'll still get 37. Either way, what's the number of waters? It's 26. So if I've gone ahead and calculated everything out for you, just for your viewing pleasure. Okay. Well, congratulations, done with the 3rd chapter. Let's move on to chapter 4.